Hi, Chuck Huber here for the Stata YouTube channel. Today I'd like to give you a relatively non-technical introduction to Bayesian statistics. The Bayesian approach to statistics has become increasingly popular, and you can fit Bayesian models using the bayesmh command in Stata. This video will provide a brief introduction to the concepts of Bayesian statistics, and you can refer to other videos for worked examples using Stata. Many of us were trained using a frequentist approach to statistics where parameters are treated as fixed but unknown quantities. We can estimate these parameters using samples from a population, but different samples give us different estimates. The distribution of these different estimates is called the sampling distribution, and it quantifies the uncertainty of our estimate, but the parameter itself is still considered fixed. The Bayesian approach is a different way of thinking about statistics. Parameters are treated as random variables, which can be described with a probability distribution. We don't even need data to describe the distribution of a parameter. Probability is simply our degree of belief. Let's consider a simple example to develop our intuition. Here I have an American quarter. This side is often called the head side, and the other side is called the tails side. If I toss the coin in the air, it must land on either the head side or the tails side, and we could use theta to denote the probability that the coin lands with the head side facing up. Since I don't have any data, I could use a uniform distribution to express the belief that the probability of heads could be anywhere between 0 and 1 with equal probability. Here I've used a beta distribution with parameters 1 and 1, which is equivalent to a uniform distribution on the interval 0 to 1. But common sense would suggest that the probability of heads is closer to 0.5, and we could express this belief mathematically by increasing the parameters of our beta distribution, which would concentrate the probability closer to 0.5. This mathematical expression of our belief about the parameter is called the prior distribution. We could also investigate the value of theta by conducting an experiment. We could flip the coin 10 times and calculate the proportion of times that the coin lands with the head side up. Here we observe 4 heads out of 10 tosses of the coin. We can quantify the results of our experiment using a likelihood function. In this case, the blue line displays a binomial likelihood function for theta given 4 heads out of 10 coin tosses. Bayesian analysis allows us to update our belief about the parameter with the results of our experiment. In simple cases, we can compute a posterior distribution for the parameter by multiplying the prior distribution and the likelihood function. In this example, the beta distribution is called a conjugate prior for the binomial likelihood function because the posterior distribution belongs to the same distribution family as the prior distribution. Both the prior and the posterior have beta distributions. Here I've plotted the posterior distribution of theta with the prior distribution and the likelihood function. Notice that the posterior closely resembles the prior distribution. This is because we used an informative prior and a relatively small sample size. Let's look at the effect of different priors on the posterior distribution. Here the red line represents a completely uninformative prior in the form of a beta distribution with parameters 1 and 1. The likelihood function is plotted in blue, but it is masked by the posterior distribution, which is plotted in black. This is an important feature of Bayesian analysis. The posterior distribution will usually be equivalent to the likelihood function when we use completely uninformative priors. The animation shows that more informative priors will have greater influence on the posterior distribution for a given sample size. And this animation shows that larger sample sizes will give the likelihood function more influence on the posterior distribution for a given prior distribution. In practice, this means that we can obtain precise estimates of the posterior distribution using smaller sample sizes when we use more informative priors. But similar precision may require a larger sample size when we use a weak or uninformative prior. We can use the posterior distribution to calculate various quantities. For example, we can calculate the mean of the posterior distribution, or the median or the mode if we wanted, and we can calculate the probability that theta lies within an interval such as 0.4 to 0.5. And similarly, we can calculate a 95% equal tail credible interval. We can also calculate a highest posterior density credible interval, also known as an HPD credible interval. The calculation of HPD credible intervals is often described as dropping a horizontal line through the density until the probability within the interval equals 95%, or 0.95. For a symmetric distribution, the equal tail and HPD credible intervals will look very similar, but they will look very different for skewed distributions. One nice feature of the Bayesian approach to statistics is that the posterior distribution from a previous study can often serve as the prior distribution for subsequent studies. Here we've used the posterior distribution as the prior for an experiment with a sample size of 100. The resulting posterior from this experiment has an even narrower distribution, and we can then calculate the posterior mean and 95% credible interval for theta. So how do we do this in Stata? Well, here I've simply typed in the raw data. 0 represents tails, 1 represents heads, and at the bottom I've tabulated the variable heads, and I can see that there are 6 tails and 4 heads. So if I wanted to fit a Bayesian model, I can go to Statistics, and then scroll down to Bayesian Analysis, and then select Estimation, and then this will open the BayesMH dialog box. So the first thing we need to do in the Model tab under Syntax is we need to select Univariate Distributions, and then under Model we need to select a dependent variable, which in this case is heads. There are no independent variables in this case. Next we need to specify a likelihood function or distribution as well as our priors. So for the distribution I'm going to select Bernoulli distribution, and then for the success probability I'm going to click Create, and I need to specify a parameter name. So I'm going to call my parameter name theta. And there's some other options here, but we'll come back and talk about those in other videos. For now I just need a name for my parameter. Then the next thing I need to do is specify the priors for my parameter, or prior. So let's click Create, and then at the top of the prior dialog box I need to select which parameter, which in this case is theta, it's the only one. And then I need to choose a prior distribution. In this case I'm going to use a beta distribution, and for shape parameter A I'm going to use 1, and shape parameter B I'm going to use 1 as well. This is the beta version of a uniform distribution. Then I'm going to click OK, and then click Submit. And in the results window, let's take a look at the command here. The command is BayesMH, followed by the dependent variable heads, and then I can see my likelihood function, specified as theta, Bernoulli likelihood with parameter theta, and then I have a prior for the parameter theta, in this case the prior is a beta 1,1 distribution. Then if I look further down in my output, I can see that the command echoes the likelihood and the prior. It also shows me some information about the MCMC iterations and so forth, and we're going to come back and talk about that in the next video. So let's just skip to the bottom here. We can see that the mean for theta is 0.4132. The standard deviation is 0.1370 for theta. Then we have our MCSE, our Monte Carlo standard error. And we also have a median reported. In addition to the mean, Stata reports the median. Then we also have our equal-tailed 95% credible interval. If we wanted to see the HPD credible interval, we can go back to Reporting, to the Reporting tab, and I can check this box that says Display HPD credible interval. So let's click that, click Submit. And now we can see that Stata has reported an HPD credible interval. So another thing we might want to do is use a more informative prior. Here we've used a beta 1,1, which is equivalent to a uniform. Let's go back to the Model tab and select our prior 1 and click Edit. And now I could change the shape parameters. Maybe I want to use a 30-30, shape parameter 30 for A and for B. Click OK. And let's click OK again. And now Stata will refit the model using a more informative prior, beta 30-30, and notice that our mean has moved closer to 0.5 because again we've used a much more informative prior that's closer to 0.5. So anyway, that's the basics of how you could do this. So I hope this was helpful. Thanks for stopping by.